All right, calculus, here we go into section 5.5. Now, 5.4, you will hopefully recall, was called Fundamental Theorem of Calculus Part 1. Today in 5.5, we're moving on to Part 2. So there really isn't anything earth-shatteringly new that we're going to be covering here in 5.5, but this is kind of a logical extension, I think, of what it was that we uncovered in 5.4. And what that was, lest we forget, was the big realization that definite integrals can be computed much more quickly, much more efficiently than people had previously thought by using antiderivatives. So 5.5 kind of completes the basic idea that derivatives and integrals are inverse operations of one another. Again, something that seems obvious to a lot of you guys because this is kind of the way that it was shown to you and explained to you last year in pre-calc. But I can assure you this was not something that was known at the time, and it was a pretty big deal when it was developed. So the fundamental theorem of calculus part 2, it looks like I've got two different formulas here. That's really not correct. They're really the same formula. It's just that the first one, and I'll go ahead and call this version A right here. This one is a little bit more relevant in a certain easier circumstance, and the second version of this formula right here in B is more universally relevant, and this is the one we're going to need in a more complex setting. But let's focus on A first. The first thing I want to point out to you guys is when it is that the fundamental theorem of calculus part 2 becomes relevant. And right here, I want you to block out everything on this page other than what is right there inside that circle that I just made. When you are being asked to take the derivative with respect to x of a definite integral. Now, let me go further. This only applies when certain things within the integral happen. It only applies when your lower limit of integration is c, which is a constant. You'll notice c doesn't show up anywhere else in this formula. But your upper limit of integration is x, which is a variable. And not just any x, not just any variable, it's the variable that we're being asked to differentiate with respect to. So that's the circumstance here in which we use fundamental theorem of calc part 2, when we're being asked to take the derivative of a definite integral with a constant for the lower limit of integration and the variable itself, x, for the upper limit of integration. Let me get rid of all that, and let me just point out one other thing that confuses people a little bit. The integrand now is not f of x, but it's f of t, and we're being asked to integrate that function with respect to that variable right there, which is t. But if you look at the end result of all this, I think you're going to realize pretty quickly what's happening. They're asking us to take the derivative of a definite integral, and what you will notice is that the end result of this is going to be the exact same function as our original integrand. The only difference is that the t, which was the variable of the original function, has now been replaced by x, which was the variable that became the upper limit of integration and the variable that we're being asked to differentiate with respect to. So in essence, you guys, the derivative and the definite integral cancel each other out, which really gets rid of that too, and we just end up with this as our final answer, only with a change in variable from t to x. All right, I'm going to get rid of all my slashes right there because it kind of muddies the waters a little bit. But that's what version A of FTC Part 2 looks like. Version B, right below it, is really the exact same thing. The only thing you will notice that's different in the entire left-hand side is that the x that was the upper limit of integration has now been replaced by a u. And this is a reminder of something we've talked about earlier in the year and we will continue to talk about later in the year, that u represents a function of x. So you would use the first version, version A of this formula, if you were asked to take the derivative of a definite integral from some constant like 2 up to just x. But you would use the second version if you were asked to take the derivative of a definite integral from some constant on the bottom like 2, not to just x, but to a function of x, like 3x squared plus 5x minus 2, or cosine of x, or e to the 5x plus 3. So if that upper limit is more complicated, if it's a function that involves x rather than just x itself, the second version is the one you will want to use. Now you will notice here that in part B, pretty much the same thing happens. The derivative and the definite integral cancel each other out. So the original integrand, f of t, becomes our answer, but with an important change. Once again, the variable of the integrand, which was t, gets replaced by not just x here, but whatever u was. And remember that u is usually a function of x. But then there's this little thing to worry about at the end, times the derivative of u with respect to x. And I hope that sounds familiar, everybody. That is essentially the chain rule showing up yet again. So as I said, this is not two different formulas, it's just two different variations of the same formula, Fundamental Theorem of Calc Part 2. So let's see it in action. Now guys, this problem right here, once we get the hang of it, it's pretty much done already. If you paid attention to what just happened, you'll notice that this circumstance is exactly what we talked about, and so the answer is the original integrand, but with the t replaced by an x. So it's x squared minus 4x. Done and done. Let's move on to the next problem. Okay, not really. If you just want to get the answer here, yeah, that's it. But I would really like you guys to understand why that works. So I'm going to go way back and take a while to explain what's happening. So you guys know that I usually like to start you off with an example for a new formula or a new theorem where that formula or theorem is actually not used, at least at first, and we can see that it does actually get us the same answer. So what I want to do with you guys is take this problem step by step and realize that we're being asked to do two things to this function right here. First, we're being asked to integrate that function. So the integral is really happening first here in brackets, and then when we get done with that integral, we're being asked to differentiate that. So let's try to break this down, and I'm going to do this in order, inside the brackets first. So, nope, that's not it, Mr. Fontana. So the d dx is just going to go along for the ride. I'll get to that in a while. And now let's start worrying about what we've been doing for a while now, using Fundamental Theorem of Calc Part 1. Let's evaluate this definite integral. So the first thing we do is anti-differentiate the integrand with respect to t. So the t squared becomes a 1/3 t cubed, or a t cubed over 3, however you want to do that. And the minus 4t is going to become a minus 2t squared. There's your antiderivative. Let me close the brackets, and we're evaluating this now from 5 on the bottom up to x on the top. So now, we're not quite done yet. We have anti-differentiated, but I need to go ahead and evaluate the f of b minus the f of a according to FTC Part 1. So this now equals the derivative with respect to x of, and here we go. Let's put the x in there first. So everywhere there was a t, it now gets replaced by an x. So that is going to be a 1/3 x cubed minus a 2x squared. That takes care of the x. Now, minus the f of a, which comes from putting the 5 in there. And this one's a little messier. 5 cubed is 125, which doesn't divide evenly by 3. So I'll just leave it as something ugly, like 125 over 3, minus, I guess this is a little better, 5 squared is 25, times 2 is 50. 50 over 3 is 100, or I should say 50 written as a fraction over 3 is 150 over 3. So that's where we're at. And now, let's go ahead and try to clean up inside those brackets. So I'm still not ready for my derivative yet. All right, I can't do anything with the first term. That's just going to remain a 1/3 x cubed. Can't do anything with the second term, minus a 2x squared. But I can combine those two like terms with a common denominator. I would get a negative 25 over 3, but I am subtracting that negative, so that becomes a plus 25 over 3. Now you guys will probably notice I did that in my head without a calculator, and it didn't take me a ton of time, but it's entirely possible it might take you a little bit longer than it took me. Well, here's the big joke. Where we are right now, you guys, all of that work that we've been doing to get to this spot right here was just evaluating what was inside the original set of the brackets right there, the original definite integral. So all of that up until this point has been using FTC Part 1. But now we're being asked to take the derivative of this new trinomial, what we got for our expression for the definite integral of what was inside. So we are going to differentiate each of those three terms. So let's do it. The derivative with respect to x of 1/3 x cubed, well, multiply the 3 out in front, drop the power by 1, that just becomes x squared. Okay, take the derivative of the second term. The derivative of a minus 2x squared is just going to become a minus 4x. And here's the real kick in the teeth, everybody. All of that work that I did to come up with this number right here, which of course is a constant, now needs to be differentiated with respect to x. And the joke of it is, everybody, that no matter what that constant was, no matter what value I used right here and put into this expression, I was guaranteed to get some constant value right over here. And whatever that constant value ended up being, as soon as I differentiate that constant, it becomes 0. So there's a big fat plus 0 that goes at the end here that will always go at the end here. And now I realize why the value of that constant did not matter. Let me go back to the first slide, everybody, and remember that whatever this c value was down on the bottom of your integral, we never used it in our final answer in either case. And this shows why. This particular c value of 5 got me a value of 25 over 3 in my integral, but when I go to differentiate that constant, it always comes out to be 0. So everybody, that was the one and only time you will ever see me bother using the constant right here, and this is where we have ended up now, everybody. X squared minus 4x, which of course is what we had a while ago when we realized that the derivative of a definite integral, assuming that you have a constant on the bottom and an x in the upper limit of integration, is simply equal to your original integrand, but we just replace those t's with whatever this variable is right here, and in a much more efficient way, we would have gotten, and we will get in the future, x squared minus 4x. Okay, same answer, whether we did it the hard way or the easy way. So my point there is, everybody, that heretofore we're going to be doing this, and all of this work down at the bottom is not going to end up being necessary, because I think that kind of shows us that A, the fundamental theorem of Calc Part 2 seems to work, and that B, that constant on the bottom is really irrelevant in the problem because we're differentiating a constant as a result, which will always drop out. So we are going to do this the more efficient way moving forward. And speaking of which, let's get to this one right here. Now, if you're a little scared by looking at this problem, well, good, that was my intention, but I have really good news for you guys. I'm hoping at this point you get the joke. What are we being asked to do here? Take a derivative with respect to x of a definite integral. And that definite integral has a constant on the bottom, and now, slightly more complicated, not just an x for the upper limit of integration, but a function of x, 3x squared. That, in effect, everybody, is our u value. So I'll write that up here. Our u is 3x squared. And that tells us, everyone, that we are going to be using, the second version of this formula where the upper limit isn't just x, but it's actually a u. So this second version tells us again that the derivative and the definite integral cancel, and that the integrand becomes our final answer. The only difference being the t in the integrand is replaced by u, which is our upper limit of integration, multiplied by the derivative of u with respect to x. So let's cut to it, everybody. The derivative and the definite integral cancel each other out. So the original integrand right here is our final answer. The difference being that all the t's now get replaced by u, which is 3x squared. Everything else, though, stays the same. So this is going to be a 7e to the 5, and the t up there now becomes a 3x squared. Keep going now. Plus 3 times the cosine of, and t was the angle, that now becomes a 3x squared as well. And then minus a natural log, and our product of that natural log was a t, and it now becomes a 3x x squared. So that is the original integrand, but now all the t's have been taken out and replaced by our u. And the only difference now, the only thing to remember is that this entire expression now needs to get multiplied by the derivative of u with respect to x, which is going to be a 6x that I'm going to try to cram right in there. So cleaning things up just a little bit, I think that 6x would look better if it were out in front. And now inside, not a whole lot going on here, guys. I can make this a 7e, and the power here is going to be a 15x squared. Woohoo, look at me go. Can't really do anything with the second term, so that's going to remain a 3 cosine of 3x squared. Gotcha. And we can't really do anything with the third term either, so I'm going to keep that as a minus natural log of 3x squared. Close the parenthesis, close the brackets, and ladies and gentlemen, we're done. Not that bad of a problem. All right, let's look at the next one right here. Derivative with respect to x of, aha! The plot thickens a little bit here, everybody. A definite integral that starts on the bottom, the lower limit of integration, of secant of x, and then goes up to the top of 10. And our integrand is cosine of t dt. So really, you guys, the challenge to a fundamental theorem of Calc Part 2 problem is recognition. Do I recognize what they're asking me to do? And if they're asking you to take a derivative of a definite integral, FTC probably applies. But it only applies if things are in the right order. If we have a constant for the lower limit of integration and a variable expression for the upper limit of integration. That did not quite happen here. Things are backwards. So what would I really like to do? I'd love to flip those two limits of integration around and put the 10 on the bottom and the secant of x on top. Can I do that? Well, there's a property of definite integrals that we learned, I believe, back in section 5.2, everybody, that says, yes, you can, but you're going to get the opposite result of what you would have normally gotten. So, hear me out for just a second, guys. Don't write this out just yet because I'm wasting a little bit of time. But what's going on here, everybody, is that the d dx, we've not been ready to even think about yet, remains. But now you're differentiating the opposite of the integral from 10 to the secant of x and so on and so forth. Now, at this point, everything I've written is correct, but now we would remember that that negative out in front of the integral is really a -1. And now I would probably apply a rule that we learned a long, long time ago that says that the derivative of a constant times a function, well, is really the same as bringing that constant out in front of the derivative and just taking the derivative of the function. So for that reason, I'm going to erase everything I've written here, and I'm going to move the negative all the way out in front of the derivative. But I did want to explain why that's okay to do. So this is the opposite now of, and I've done it again. Don't do that. There we go. Okay, so let's try it again here. The opposite of the derivative with respect to x of the definite integral from 10 on the bottom to secant of x on the top of the cosine of t dt. And now things are where we want them to be. Let me ignore the negative for right now and deal first with the derivative of a definite integral with a constant on the bottom and a function on the top. That means that we can apply FTC Part 2, but of course the negative just rides along here. So the derivative and the definite integral cancel each other out. Our answer is the integrand, cosine, but the angle now changes from t to whatever that upper limit of integration was. So this is now the cosine of the secant of x. But wait, there's more, times the derivative of that upper limit of integration. And our derivative of secant of x, everybody, is going to be a secant of x multiplied by a tangent of x. So that is going to take care of all of that. And let's run with this and see if we can't clean it up. Now, this is always a funny one every year. I ask people, is there anything we can do to clean up what's happening inside? And a lot of people want to say that the cosine and the secant right here are going to cancel each other out. That, I'm afraid, is incorrect. What would be the case is if we were taking cosine of a particular angle and multiplying multiplying it by the secant of the same angle. Then what would happen, guys, is whatever your cosine ratio is, let me just call it A over B, secant is defined as the reciprocal of that same ratio, B over A, and everything would cancel, and you would just end up with 1. But that is not what's happening here. We are not taking cosine of x times the secant of x. We're supposed to take the secant of x, which gives us some goofy ratio, and then take the cosine of that ratio. So for example, the secant of x, let's just pick a nice angle out there like pi over 4. The secant of pi over 4 is the square root of 2. You would then be taking the cosine of the square root of 2, and that's not one that we just know. So, long story short, too late, what we had here doesn't really simplify at all. Nothing cancels here. Let me think real quick about what's happening here. Secant is 1 over cosine, I should say 1 over cosine of x. Tangent of x is sine of x over cosine of x. Those both have a cosine of x on the bottom. So no, nothing cancels there, and that means, everybody, I'm actually perfectly fine with this answer right here. I really don't think that it can be simplified at all. I guess getting rid of the brackets would make it look a little nicer, but whoopity-doo, you just have a negative out in front. So there you go, problem solved, and there's our answer. So okay, we're good with that one. Okay, one more in this style of problem before we move on to the goofy thing that comes at the end. All right, so let's do this one right here. And I think right away you can see why this one is tougher than the last 3. Now again, we're being asked to take a derivative of a definite integral, but FTC Part 2 only applies when the integral you're taking has a constant on the bottom and a variable expression up on the top. Now, on the last problem, we had to switch things around. On this problem, we have the issue that there's a variable expression on both the top and the bottom. So what we are going to do now, everybody, is rewrite this here using a property that we learned earlier in the chapter called the additivity property for adjacent integrals. We're going to take a derivative with respect to x of, and what we're going to do now, and you guys will get efficient at this in the future and be able to skip some steps. But for now, guys, I'm going to break this integral up into 2. The first one, my hand is really creating problems today. I need one of those gloves. Anyway, the first integral has a negative 5x on the bottom, and we're going to put some random arbitrary constant value called a up at the top. The integrand stays the same, 8 minus 2t with respect to t. And we will add to that another definite integral that starts exactly where the first one left off. That would be at a and ends up here at 2x cubed, and the integrand remains 8 minus 2t dt. So all of this is predicated on the idea that a is somewhere in between negative 5x and 2x cubed. You'll notice I didn't use a 0. A 0 would only work if this term right here were negative and this term right here were positive, or at least if they had different signs. And while it looks like that is probably the case, it won't always be that obvious, and there's really no point in making that assumption. So we're just going to go with a. Now, if you take a look at what's going on, this second integral right here is exactly what we want it to look like. Constant for the lower limit of integration, there's your a, and a variable expression for the upper limit of integration. Okay? But the first one is now backwards. So, this is what I meant when I said some of you guys will sniff this out right away and you can save some time. I now need to apply that changing limits property here that we used in example C. So this is now the opposite of the integral from a to a negative 5x of 8 minus 2t dt plus the definite integral from a to 2x cubed of the same integrand, 8 minus 2t, not a very good minus sign, taken with respect to t, and there we go. And now, everybody, we're in pretty good shape. The derivative applies here, and it applies here, but don't lose sight of that negative right there, which can be a little tricky. So, here we go. The derivative and the integral cancel each other out, but the negative stays there. And the integrand is now our answer, 8 minus 2, but the t gets replaced by your u, which is a negative 5x. So that takes care of the first integrand. Now, I did something dumb already, even though I was talking about it. That negative, I did remember to bring it out in front, but I should have put brackets right there. And in a moment, you guys can see already that that negative is going to need to get distributed to everything else that was happening inside. All right, no such problem over here now. This is a derivative of an integral straight up, so our integrand, 8 minus 2t, is our answer. But again, the t gets replaced by your upper limit of integration, which is a 2x cubed. And what did I forget to do in both cases? That whole integrand needs to get multiplied by the derivative of the upper limit, which here is going to be a 6x squared. And here, as I forgot to do, is going to be a negative 5. So I'm going to cram that negative 5 in right there. Sorry, guys. And we'll have to clean that up. So, didn't leave myself a ton of room, and I'm not sure if I can... I did learn that little trick right there. Maybe I can, I think if I just draw something down here, now I can zoom in on it again. There we go, and get a little lower. Look at me learning some new things. All right, so this first expression, the negative 1 out in front and the negative 5 are going to make a positive 5 that we're going to distribute inside here. So the 5 times 8 is going to be a 40. This term right here would have been a plus 10x. Let's distribute the 5 in there and get a plus 50x. Got it. And now for this next one, that negative 6x squared kind of needs to get backwards distributed in there. And boy, I wrote over it, but that was a plus sign right out in front. That's this symbol right here. So where are we, guys? The 6x squared times the 8 is going to be a plus 48x squared. This term right here would have been a negative 4x cubed. Let's multiply a 6x squared by that, and that should get us a negative 24, and x cubed times x squared is going to be x to the 5th. Now, that polynomial right there, a 4-term quintic polynomial, is in the exact opposite order of what I would normally like to see it as, but nobody cares at this level. There's no rule that says you have to write a polynomial in descending order, so I am perfectly fine with that answer right there, and it doesn't look like it can be simplified any further than that. Now is probably not a terrible time to tell you guys something that I think you know, although I'm not entirely 100% sure. Your graphing calculators, everybody, will do all of this work for you. Now, I tell you this knowing that on quizzes and tests, I'm going to have to see all of this work in order for you guys to get full credit, but let me show you what that would look like. So, where can I find my calculator? Here we go. Education category. Here's our Inspire CAS. And let me open up a new calculator page. Hey, and here we are. All right, everybody. So if we go back to the original problem, what was going on here? We were being asked to take the derivative of a definite integral of this whole mess right here. Our calculators will do that for us. How? Well, I am going to go, there's a couple of different ways we could do this. On my app, everybody, I have got a button right here. You can see me shading that right there. And if I click that button, that'll get me to a derivative page. You guys have that option somewhere too, but probably the more typical thing you're going to do is hit your menu button. And for me, that's this little wrench icon right up at the top. And then you guys are going to hit, I believe, 4 for calculus, and then number 1, I believe, for derivative. So let's fill some things in. We're being asked to take the derivative with respect to x of, and now we would hit tab or the right arrow, and now the function we're differentiating, that's an integral. So I'm going to hit menu again. And notice I'm still on calculus here. You guys would probably have to hit 4 one more time, and then we would do a definite integral. And this integral, I have forgotten already what it looked like, started at negative 5x and went to 2x cubed up on the top. So let's do that. Lower limit of integration, negative 5x. Again, hit the tab, or I thought for you guys the right arrow would have worked, but for me I got to hit the up arrow. And then it went to a 2x to the 3rd power. Gotcha. And now our integrand, everybody, was 8 minus 2t taken with respect to t. So in the middle here, 8 minus 2, and I think I have a t hiding there, okay, with respect to t. So let's see if the calculator gets the same answer that we got. A negative 24x to the fifth plus 48x squared plus 50x plus 40. Yep, exactly the same answer that we got here. So you guys have this resource available to you to check any of your answers, although of course you have all the answers and the solutions manual all worked out. But, you know, if it were a test or a quiz question and you were allowed to use your calculator, that's a way you could check your answer to make sure that you had it right. All right, everybody. Now would be a great time to stop and pause if you're getting a little bit restless and you wanted to start some of the homework. But I'm going to move on into this last concept that we are going to talk about here. And this is something I've actually just added to the notes within the last couple of years. And this is a concept that is going to show up quite a bit, ladies and gentlemen, as we get ready for the AP test in May. They have defined a function here, a of x, as being the definite integral from 0 to a variable here, x, of another function, f of t, taken with respect to t. Now, as this problem exists right now, nothing here should jump off the page and tell you use FTC part 2. We only use FTC part 2 when we take the derivative of a definite integral. And they're not asking us to take a derivative right here, so let's not fall for that. They're just saying that a of x is defined as the definite integral from 0 to x of this function here. And you'll notice, guys, that's the function that's been given to us. It's this weird, goofy, segmented, piecewise function that starts at 0, and it ends, it looks like, at x equals 10. Now, the real questions are going to come in parts B and C. But for part A right now, I just want to get a handle on what exactly is happening here by asking you guys to complete this table. So for these 11 values of x, we're supposed to figure out the value of each one of them. So I'm not going to write them all out, guys, but the first thing they're asking us to do is when x is 0, find a of 0. So again, I won't always write this out, but just for starters, a of 0 means that I take this function right here and I replace that x with a 0. So this becomes the integral from 0 to 0 of f of t dt. Now, I'm hoping you don't have to think real hard about this one. This is a property from 5.2 that we learned called the same limit property. And what is effectively happening here, guys, is we are trying to measure, let's go back to 5.2, we're trying to measure the net area between this curve and the x-axis starting right here at x equals 0 and ending, come on now, at wherever I put this red line, which in this case is also 0. Well, as I think you guys can see, there is no area in between the green line and the red line, so that answer is going to be 0. Okay, doesn't matter what function you're dealing with, if your limits of integration are the same, the net area between those, the starting and the ending value, will always be 0. Okay, next one. And again, we're not going to write all of these down, but just to get the hang of it, a of 1 is asking us to take the definite integral, starting at 0 always and ending at 1, of f of t dt. Now, you guys, we've learned a lot of tricks here for how to calculate definite integrals over the last couple of sections, but none of those tricks are any use to us here at all because we don't have an explicit definition for what our integrand f of t is. So I can't anti-differentiate, although I could here because I think I know what that function is. Kind of looks like y equals 3. But regardless, that's not going to help me once I start moving on into the other parts of this function, which look like they're all completely different. So we're going to go back to what we were doing at the beginning of this chapter, and we're going to look at the definite integral as being the signed or net area between the curve and the x-axis, starting at x equals, in this case, 0, and ending when x is 1. So what are we doing, guys? We are looking for the area of this region right here. And as I think you guys can tell, this one's pretty easy to find. What I just shaded there in purple is a rectangle with a base of 1 and a height of 3. I'm pretty good at geometry, guys. I'm pretty sure the area of that rectangle is 3. So guess what? That's the value of a of 3. By the way, if you haven't figured this out yet, the reason they're calling this function a, this is an area problem. Let's move on. Now, this is the last one I'm going to write here. A of 2, then, is the definite integral from 0 to 2 of f of t dt. So it's the exact same concept we were just doing, except now I'm extending that right border now from 1 to 2, which means my answer also needs to include that region right there. Well, now it's a 2 by 3 rectangle, so that value is 6. And boy, look at my y values now. 0, 3, 6. They seem to be increasing at a constant rate, which means that a of x is probably what kind of function? That would be a linear function, which is true because f of x looks like a constant between 0 and 2. And a constant function has a linear antiderivative. All this makes some sense if you think about it that way. But now let's move on. Now we're sliding this thing over to 3, and the plot thickens a little bit. Now I've got to add, I'm going to switch a color on you guys right here. Let's go green. Now I'm going to add the area of this little trapezoid right here to what we had before. That area of 6 right here has not gone away. It's still there, but we need to add the area of that trapezoid to it. All right, guys, so where are we? I don't think I made your life really easy. It looks like this point right here probably occurs at a height of 1.5. So my formula for area of that trapezoid right there would be 1/2 times its base, which actually runs horizontally here, which is 1, times the sum of its bases. The base on the left here has a height of 3, and the base on the right over here, has a height of 1.5 or 1.5. I'm going to make that 3 over 2. So this is a little bit ugly. 3 plus 3 over 2, that's 4.5 or 9 over 2, times 1 times 1/2 is going to get us 9 over 4 for the area of that green trapezoid. That is 2.25. We are going to add that to the 6 that we had prior to this, everybody. So that 6, we are going to add 2.25 to, and it is going to be 8.25. And I hope I don't get too many more fractions because that was hard to fit in that box. That's where we're at. Let's keep going. This actually gets easier now. As I move this thing, that's not what I wanted to do. As I move this red line further to the right now, my trapezoid just kind of morphed into a nice triangle, which is actually much easier to deal with here. So that trapezoid now becomes this triangle. Okay, and the area of that triangle here, guys, 1/2 times a base of 2 times a height of 3. So that is going to get us 3 for the area of that triangle. Add that to the 6 that we had before, and our integral now becomes a 9 for a of 4. Okay, what happens next? Kind of interesting. We slide this thing over to 5. No, there we go. We slide this thing over to 5, and what have we gained or lost? Absolutely nothing. This function rides the x-axis here for a while. It has no additional area, either above or below the x-axis. So there's no net change from 4 to 5. A of 5 is still 9. And guess what? As we slide over to 6, once again, there we go. At 6, once again, there's no net change. A of 6 is still 9 as well. But now something interesting starts to happen. Now, as we get to 7, everybody, there we go, we now have some area underneath the x-axis. So we need to take the number where we were just a moment ago, which is 9, and now we're actually subtracting area because our region now goes below the x-axis. So it looks like the area of that one triangle that I just shaded in red would be 1/2 times a base of 1 and a height of 2. So the area of that one triangle is 1. And because this region here is below the x-axis, we're going to take our existing value of 9 and subtract 1. So the integral of the value of a of 7, I should say, is now going to be back down to 8. We're actually losing net area because we're adding negative regions, is a good way to look at it. And what happens now as we move on to 8? More of the same, everybody. We are now adding additional negative area, actually the same amount that we had just a second ago. So we're going to subtract a 1 again, and now that's going to tell us that a of 8 is equal to 7. An interesting thing happens here. Now, as we move to 9, let's take a look at what happens. Now we're back in the green, everybody, to use some business language, okay, or in the black, I guess is what they would say. We are now adding positive area now up above. But what I want you guys to notice here, this is going to get a little tricky, guys, is that this positive region that we're adding right here is the exact opposite of that negative region that we just added there. They effectively cancel each other out. So the value of a of 9 is going to be identical to the value of a of 7. Okay, where we were 2 steps ago right here, well, we lost some more for a of 8, but then we gained it right back for a of 9. So this value here for a of 9 will be the same as a of 7. That'll be 8. And the last one, some of you will find this very easy, some of you find it a little bit difficult. Now this function unnaturally jumps down to a y value of -4. That now means, you guys, let me go here again. That now means that we are adding additional negative area right here to wherever we were just a moment ago. The area of that red rectangle that I just shaded is 4, and because it's below the x-axis, that means that we're now adding a -4 to our previous answer of 8, and that ends us up at 4 for our value of a of 10. All of that, you guys, was really just meant to get your feet wet a little bit with how to work an area function if a of x is defined as a definite integral from 0 to x. Now, lucky for you guys, the next 2 questions aren't going to be that hard to answer. So it's the exact same setup. Sorry, I had to move some things around here because my formatting got ugly. We're supposed to find the maximum value of a of x on the interval from 0 to 10, and this is something we're going to have to get used to this year. The directions also say to justify your answer. So let's take a look at it. What people are going to do is they're going to say, wow, I just did all this work over here in part A to find 11 different values of a of x. And if they want the maximum out of all of those, I just need to look at my chart right here, and I need to say, what is the biggest value that a of x ever became? Well, as I read through it, it looks like 9 is the biggest value that we ever got. So a lot of people are going to want to say that the maximum value, nope, that's not it, that the maximum value of a, so I'm just kind of making up my own notation right here, but a max is equal to 9. That, ladies and gentlemen, is the correct answer. The only problem is this part right here that says justify your answer. And what I need to remind you guys of is something right here that is really easy to forget. What we're doing right here is we are only looking at the value of a of x at 11 different points. Now 11 sounds like a lot, okay? But ask yourself, how many x values are there in this interval from 0 up to 10? The answer to that is infinitely many. So in that regard, we didn't really look at very many. 11 out of infinity, I'm pretty sure is not a real great percentage. So all that we've considered here so far is the idea that a maximum may have occurred at an integer value of x, but there's absolutely no guarantee of that. So the way that we justify our answer here guys. And again, I drew the green and the red arrows here again, but the way we justify our answer is going to be much more technical than that, but not really all that difficult. So if you remember, guys, we started at 0. And at a of 1, we were adding area. We were at 3. Then we jumped up to 6. Then we jumped up to something like 8 1/4, I thought. It kept getting bigger and bigger and bigger. And then at a of 4, I think we got up to 9. Am I right? Yeah, that's the first time the 9 showed up. Then what happened? Well, nothing happened for a of 5 and a of 6. But then our value actually started getting lower. Why? Because we were adding negative area. And that continued to decrease our value of a of x up until we got to a of 8. Then we started adding more positive area back, so a of 9 was bigger than a of 8. But then a of 10 brought us down further because we added negative area. What I need to really remind you guys of, though, is to justify our answer that a function, I'm going to write this up here in the corner here, that f of x has a maximum. And I won't say whether it's an absolute or a relative. We'll have to test that in a minute. But f of x has a maximum where its derivative, f prime of x, changes. And I'm going to say changes sign, but I'm actually going to be more specific than that. A maximum specifically occurs where a function's derivative changes sign from positive to negative. So one of the fundamental things that we learned in the first semester is how to use a function's derivative to determine where that function has extreme values and critical points. A maximum occurs where a function's derivative changes sign from positive to negative. And so we were given information about a of x, but if we want to find a maximum, we really need the derivative of that function. So a prime of x, everybody, is defined as the derivative with respect to x of a of x, which means it's the derivative with respect to x of the integral from 0 to x of f of t dt. Oh, and maybe that's why we're talking about this in section 5.5. We're being asked to take the derivative of a definite integral with 0, or any constant really, for its lower limit of integration, and x for its upper limit of integration. Okay, Mr. Miyagi, now I understand. So that's going to equal the derivative and the integral cancel each other out, but that t gets replaced by that x, and we end up with f of x itself. Okay, so that's where we were. A of x was defined as that. So what we have here, guys, is that f of x, let's ignore all the noise here, f of x is the derivative of a of x. And I really want to come back to this idea. A maximum value of a of x will occur where its derivative, a prime, which is f of x, which is the graph that we're looking at right here, where this function changes sign from positive to negative. Where does this graph change sign from positive to negative? Well, I messed with you a little bit right here, but it kind of happens right here. All right, and it also happens again right here at 9, where this function was either positive or, in this case, 0, and then it became negative, and the same thing happens here at 9. Prior to 9, f of t was positive. After 9, f of t was negative. So your only potential answers here, guys, would occur at a of, and I think that was a 6 if I'm not mistaken, okay, or at a of 9. And if I go back to my table here, a of 6 was 9, a of 9 was 8. So 9 and 8. These are my two potential maximum values. What we can find here, guys, is that only one of them is actually the biggest, and that's this one right here. So that, everybody, justifies the answer. What you have right here for 9, let's go back to the beginning of chapter 4, guys. This is your absolute maximum. And right here, that 8 is what we called a relative maximum. Higher than the values directly around it on either side, but not the big kahuna for the entire thing. All right, that's how you justify that answer. Now, really the same problem here on 3, but now they're asking us to find a minimum. So let's recall, everybody, that a generic function, f of x, has a minimum value where, and it's the same basic concept now, guys, but it's reversed, where its derivative, f prime of x, changes sign, okay, from, and a minimum now occurs when your derivative was negative and then becomes positive, where the behavior of the function changed from decreasing to increasing. So if we recall, everybody, that the derivative of a, that a prime of x, is just going to equal f of x, which is this graph right over here, we just need to find where this graph changes sign from negative to positive. And the only spot where this function was negative but then becomes positive is right here at 8. That's the only one. So I know already, everybody, that our absolute minimum value here occurs at, it would be the value of, no, Mr. Fontana, not f, it would be a of 8. And the value of a of 8, let me go back to my table right here. Ooh, hang on now. Looks like it's going to be 7. Okay, that is going to be 7 here. All right. Let's take a look at why that answer isn't right. And I realized it as soon as I had it right here. If I go back and look at this the easy way, 7 does not appear to be the minimum value in this table. I've got, let's see, a 4, I've got a 6, I've got a 3, and I've got a 0 there as well. Okay, I see what I did wrong. This, everybody, is not an absolute minimum. This right here is a relative minimum. Now, what I have found right here, let me go back to what I was saying, which was not entirely wrong. This is the only spot within the interval where a minimum could occur. But if we remember back something else that happened in chapter 4, everybody, an extreme value, a max or a min, can occur at critical points or endpoints. So, and I should have done this on my last example too, I apologize for that, we also should be considering our endpoints, a of 0 and a of 10. And now I see the error of my ways. A of 0 was 0, and a of 10 ended up being 4. So now that we look at these 3 potential minimums, we choose the lowest out of those 3, and 0 is actually our minimum value. That makes a little bit more sense, Mr. Fontana. All right, if we go back to the chart, I think we can find there was never a spot. Oh, this is messy. Let me get rid of all this junk. There was never a spot, as I was sliding that red line from left to right, never a spot where this region here, oh, I erased my function. Let me do that here. There was never a spot here where this function had more area underneath the x-axis than it had above the x-axis. So it was never going to go negative. 0 then is the lowest. And to my point, everybody, atoning for my mistake earlier, I should have also checked endpoints here as well. Now, those values didn't change at all, but in some problems, those might matter. A of 0 is 0, and a of 10, what was it again? I forgot already. A of 10 was equal to 4. So now, with that, and then let's see, that, and that, those 4 values, the 2 endpoints at 0 and 10, and the 2 critical points at 6 and 9, we would choose the largest out of those 4 y values, and that is why a of 6, which gave us a value of 9, was actually our absolute maximum. So I forgot something that I would have yelled at you guys for forgetting, that an extreme value, a max or a min, can occur at critical points or at endpoints. When I did 3B the first time, I was thinking about critical points. I wasn't looking at endpoints, and that's something we are going to need to do, and example C shows why that's so important. So that our minimum value here was 0, that one having come at an endpoint, not a critical point. Okay, everybody, long section there on 5.5, but give that homework a try and let's see how you do.